Our bodies inhale two gases, oxygen and nitrogen. Oxygen is essential for life. We also generate gas, carbon dioxide. It's a byproduct of metabolism, and most of us think of it as a waste product, but its progeny, bicarbonate, has major roles in metabolism, in acid-base chemistry, and the maintenance of extracellular osmolality. This tutorial will look at the solubility of carbon dioxide and bicarbonate in extracellular fluid. Fundamentals of Anesthesiology and Critical Care, with me your host, Pat Nelligan. Understanding gases and vapors. We're now on to part 2 of solubility of gases and liquids, and this tutorial is about carbon dioxide solubility. In the previous tutorial, we talked about the basics of gas solubility, Henry's law of gases dissolved in liquids, the Ostwald solubility coefficient, and I showed you the solubility coefficients of oxygen, carbon dioxide, and nitrogen in extracellular fluid. In this tutorial, we're going to look at carbon dioxide solubility. I'm going to start with a discussion about extracellular compartments and fluid distribution, followed by carbon dioxide metabolism, CO2 solubility and partial pressure, the CO2 content of blood, plasma, and extracellular fluid, and the impact of temperature on carbon dioxide content, in particular with respect to hypothermia. But first, this. I want to carefully explain what I mean by extracellular fluid and the distribution of liquids in the extracellular space so that everything that follows in these tutorials is clear. Most doctors misunderstand this. Roughly 2/3 of body weight is made up of water. 2/3 of that water is in the intracellular space and 1/3 is in the extracellular space. The extracellular space is divided into two compartments, the interstitial space and the intravascular space. Intravascular fluid in someone with a hemoglobin of 15 grams per deciliter, that represents a hematocrit of 45%, or red cell mass, is 45% intracellular fluid and 55% plasma. Only the plasma is extracellular fluid. That means that plasma volume is only 20% of extracellular fluid volume. For an 80 kilogram male with 16 liters of extracellular fluid volume, that means that the plasma volume is 3.3 liters and the interstitial volume is 12.7 liters. It's also important to understand that plasma and extracellular fluid are not identical. This is because of Gibbs-Donnan effects on electrolytes and concentration gradients between gases and other metabolically active substances. The main waste product of the body that is generated by cells is carbon dioxide. So for the rest of this tutorial, we're going to look at CO2 and how it dissolves in extracellular fluid and plasma. Almost all of the carbon dioxide in the body is produced by oxidative metabolism in the mitochondria. The carbon dioxide that is dissolved then exits the mitochondria and the cell and enters the interstitium. The partial pressure of carbon dioxide, if you were able to measure it in the interstitium, is approximately 6.7 kilopascals or 50 millimeters of mercury. Most of the carbon dioxide that exits the mitochondria actually goes into red blood cells or erythrocytes, where it is hydrated with water in the presence of carbonic anhydrase to carbonic acid. Carbonic acid then rapidly dissociates to release the equivalent of hydrogen ions, some of which bind to hemoglobin, and bicarbonate, which is pumped out of the cell in response to chloride entering the cells. That's the hamburger shift. The bicarbonate concentration of extracellular fluid is 24 millimoles per litre. It is imperative that all healthcare practitioners understand that bicarbonate and carbon dioxide are the same thing. Bicarbonate can be easily changed back into dissolved carbon dioxide with the addition of a single hydrogen ion. We now have two versions of carbon dioxide. One is a dissolved gas that behaves like a gas, but there are no bubbles of gas, just molecules. The other is a charged particle. They do not behave the same. Gases flow from where they're in high pressure to where they're in low pressure, and flow stops when the pressure equalizes. Solute molecules diffuse from where they're in high concentration to where they're in low concentration, and the diffusion stops when the concentrations equalize. Concentration is measured in millimoles per litre. However, if, for example, there is a cellular membrane between two compartments, charged solutes cannot pass easily from one compartment to the next, but osmotic pressure must be equal between the two compartments. So bicarbonate does not pass easily between the cellular space and the interstitial space. Gases dissolve in liquids along partial pressure gradients according to Henry's law. The movement of gases stops when the partial pressure gradients equalize. Gas pressure in liquids is measured in kilopascals or millimeters of mercury. There is a huge difference between the molecules that are normally gases and the molecules that are solute. Carbon dioxide is always a gas, and when dissolved in a liquid, it remains a gas, not as bubbles of gas, but as molecules of gas embedded in liquid. Bicarbonate is always a solute. It is dissolved in the liquid and has an osmotic effect. In this example, we have both carbon dioxide and bicarbonate dissolved in a liquid. It's kept in a container under pressure. Gases always want to escape the liquid, but are being constrained here by Henry's law. The pressure being applied by the container being sealed. Outside the container, the partial pressure of carbon dioxide is extremely low, just like in the atmosphere. Once the lid of the container is removed, the carbon dioxide rapidly escapes along the partial pressure gradient. The bicarbonate stays put. This is exactly what happens when you leave the lid off a bottle of mineral water for a while. It goes flat and tastes salty and sour. This is a cartoon to represent two separate fluid compartments in the body. On the top in yellow is the interstitial fluid that has an osmolality of 300 milliosmoles per litre. At the bottom in pink, there is the intracellular fluid that has an identical osmolality of 300 milliosmoles per litre. These two compartments are separated by a cellular membrane that is permeable to carbon dioxide but impermeable to charged solute. Into these compartments we're going to put three things: carbon dioxide that's dissolved, bicarbonate, and intracellular anions such as phosphate. At this point in time, all things are equal. There is an equal osmolality between the two compartments, so the bicarbonate and the phosphorus stay where they are, and the carbon dioxide tension is equal between the two compartments. But that's not how the body works. Now the carbon dioxide tension in the intracellular compartment is 8 kilopascals or 60 millimeters of mercury. In the interstitial compartment, it's 6.7 kilopascals or 50 millimeters of mercury. So there is a partial pressure gradient between the intracellular and extracellular space. And as a consequence, carbon dioxide diffuses across the cell membrane until the pressures are equal. But they are never equal, as mitochondria continuously produce carbon dioxide and the venous capillaries continuously clear carbon dioxide. Remember These gradients are always pressure gradients in kilopascals or millimeters of mercury, not concentration gradients. Importantly, those charged particles, the electrolytes, will remain in their compartments. They won't budge unless actively transported into cells or out of cells via transcellular ion pumps. Now, let's look in more detail at the partial pressure gradients of carbon dioxide between the mitochondria and the airway. In this cartoon, we have the mitochondria, the intracellular space, the interstitium, the venous and arterial capillaries, venous blood, the alveoli, and arterial blood. The partial pressure of carbon dioxide in mitochondria is 9 kilopascals or 67.5 millimeters of mercury. In the cytoplasm of the cell, it's 60 millimeters of mercury or 8 kilopascals, so the CO2 diffuses out of the mitochondria. In the interstitium, the partial pressure of CO2 is 6.7 kilopascals or 50 millimeters of mercury, so the dissolved CO2 passes through the cell membrane into the interstitium. There is a further gradient from the interstitium into the venous capillaries, so carbon dioxide enters venous blood, and the partial pressure of venous blood is 6 kilopascals or 45 millimeters of mercury. It then leaves the liquid phase and passes into the gas phase in the alveoli, where the partial pressure is 5.1 kilopascals or 38 millimeters of mercury. And in arterial blood, the partial pressure is 5.3 kilopascals or 40 millimeters of mercury. That's what you see on an arterial blood gas. You might ask, though, that as carbon dioxide has a molecular mass, it must have a concentration that's measurable in millimoles per litre. And I'm going to give you these numbers as an academic exercise. We never use these numbers in clinical practice. The mitochondrial CO2 concentration that's dissolved is 2.08 millimoles per litre. In the intracellular space, it's 1.85 millimoles per litre. In the interstitium, it's 1.55 millimoles per litre. In venous blood, it's 1.4 millimoles per litre. It's only a gas in the alveoli, and in arterial blood, it's 1.22 millimoles per litre. How do we calculate the total quantity in mils of carbon dioxide that is present in plasma? So in all these examples, we are going to take a 80 kilogram male with 16 litres of extracellular fluid volume, of which 3.3 litres are plasma and 12.7 litres are interstitial fluid. And plasma is 50% arterial blood and 50% venous blood. The PaCO2 of the arterial blood is 5.3 kilopascals or 40 millimeters of mercury. We're going to multiply that partial pressure by the equivalent solubility coefficient, for example, 5.3 times 5.18, and the result is 27.45 mils of carbon dioxide per litre of arterial plasma. The mixed venous carbon dioxide is 6 kilopascals or 50 millimeters of mercury. We'll do the same calculation. 6 times 5.18 is 31.08 mils of carbon dioxide per litre of venous plasma. If we add the two of these and divide by 2, we find that the average CO2 content per litre of plasma is 29.27, and we multiply this by 3.3, and the result is 96.6 mils of carbon dioxide in this patient's plasma. Let's look at the total extracellular CO2. That means we must calculate the interstitial CO2 content using the same calculations. We know the interstitial volume is 12.7, and the interstitial partial pressure of CO2 on average is 6.7 kilopascals. Calculation is 6.7 times 5.18 times 12.7, and that means that there are 440.7 mils of carbon dioxide in the interstitium. Have a go at calculating out these numbers using millimeters of mercury. Multiply the kilopascals by 7.5. Here's a calculation The result you will receive won't be identical to the one above because there's also a little bit of variance when you're converting from millimeters of mercury to kilopascals, and a lot of these solubility coefficients have multiple numbers after the decimal point, but you get the idea. So let's put the plasma and the interstitial CO2 content together to find the full extracellular volume of dissolved carbon dioxide. We have 96 mils in plasma, we have 440.7 mils in the interstitium, so the total dissolved CO2 is 537.5 mils. So you have half a litre of carbon dioxide in 16 litres of extracellular fluid. That works out at 34 mils per litre. This number grossly underestimates the amount of carbon dioxide dissolved in extracellular fluid because of the bicarbonate. And bicarbonate can be turned into CO2 gas. And we can calculate that out by calculating out the molar volume. At standard temperature and pressure, 1 mole of gas occupies 22.4 litres, 1 millimole occupies 22.4 mils. Now with this in mind, it's worth noting, as I previously mentioned, that CO2 dissolved in plasma is conventionally measured in kilopascals or millimeters of mercury, but it can be measured in millimoles per litre, and there is a solubility coefficient. In millimoles per litre per kilopascal, that solubility coefficient is 0.231. In millimoles per litre per millimeter of mercury, it's 0.03. From previous numbers, I've demonstrated that the average PCO2 is about 6.5 kilopascals or 50 millimeters of mercury across the entire extracellular fluid. And we can take our molar volume calculations to figure out how many millimoles of carbon dioxide are present. And that's worked out by 6.5 multiplied by 0.23, that's in kilopascals, or 50 times 0.03. or 1.5 millimole per litre. So that's our average carbon dioxide concentration in extracellular fluid. Let's figure out what the total carbon dioxide concentration is in extracellular fluid. And I will point out that this part is totally conceptual. This isn't reality because I'm going to be talking about solute as if it were a gas. Bicarbonate is never a gas, CO2 is never a solute, but bicarbonate, when you add a hydrogen ion, turns into carbon dioxide and water. So it does become gaseous under certain circumstances. But as bicarbonate, it's not a gas. But we can calculate out the carbon dioxide content and the volume of carbon dioxide that it would take to make this bicarbonate theoretically. So the average dissolved CO2 is 1.5 millimoles per litre, and the bicarbonate is 24 millimoles per litre. So now we have 25.5 millimoles per litre of theoretical carbon dioxide. If we multiply this by 22.4 mils per millimole, then we get 571.2 mils of carbon dioxide per litre of extracellular fluid. Our patient has 16 litres in their extracellular space, so that's multiplied by 16, or 9 litres of carbon dioxide in total dissolved in extracellular fluid. And that is a lot of carbon dioxide. And the reason why there's so much carbon dioxide there is because of its conversion into bicarbonate. Now let's move on. What impact does changing temperature have on carbon dioxide solubility? Here is a rule of thumb. As liquids heat, they release more gas. As liquids cool, they suck in more gas. So for every 1 degree Celsius increase in temperature, there is a just under 3% reduction in the CO2 solubility in blood. For every 1 degree reduction in temperature, there is a just under 3% increase in the CO2 solubility in blood. So you can see in this particular table that at 37 degrees Celsius, the solubility coefficient in mils per litre per kPa of carbon dioxide is 5.18, but it increases to 6.21 at 30 degrees Celsius. And that means that the volume of carbon dioxide dissolved in 1 liter of plasma goes from 27.5 mils to 33 mils as you go from 37 degrees to 30 degrees Celsius. And this is linear. As the temperature goes up, the CO2 content goes down. As the temperature goes down, the CO2 content goes up. So if we go from 37 degrees, which provides us with just under 28 mils per liter dissolved of CO2, to 30 degrees, that gives us 33 mils of CO2 dissolved per liter of blood. You can see that the CO2 content increases. Let me give you an example of a situation that you might encounter. Nathaniel was out at a Christmas party on a bitterly cold night. He was showing off to his friends and fell off a wall into a river. When he was rescued, he was severely hypothermic. His core body temperature was 30 degrees Celsius. What would you expect his blood gas to look like? This is Nathaniel's blood gas in millimeters of mercury. I'm showing you the normal blood gas at 37 degrees on the left, and on the right, we're showing you the uncorrected blood gas at 30 degrees Celsius. I'm now going to give you the same blood gas in kilopascals, and depending where you are viewing this, you can choose which blood gas to look at. And what you will immediately notice on this blood gas is that the pH has gone up. It's now 7.55. The PaCO2 has fallen to 4.40. The PaO2 has fallen because carbon dioxide and oxygen are more soluble in cold blood. The bicarbonate goes up a little bit and the patient looks like they have an alkalosis. There is a positive base excess. This can be grossly misleading, and this is horribly misunderstood by the vast majority of anesthesiologists, because the question they ask is, why is the PaCO2 lower despite the greater dissolved CO2 associated with increased solubility in hypothermia? Well, you fundamentally understand this. This is a problem of how blood gas machines measure blood gases. If you have 2 bottles of cola and take the cap off both, you're going to leave one on the counter and one goes back in the fridge, and you leave them there for about an hour or so. When you come back, the bottle that's been left in the fridge is still fizzy. The one that was left on the counter will have gone flat because the carbon dioxide will have escaped. The lower temperature in the fridge keeps a lot of the carbon dioxide dissolved. The partial pressure of CO2 that we measure using a blood gas machine is related to how much gas escapes from a solution from the liquid phase to the gas phase. At lower temperatures, carbon dioxide is held more tightly in the plasma, so fewer carbon dioxide molecules escape as a gas. This lowers the measured partial pressure, and that's why the PaCO2 measured at 30 degrees uncorrected is lower than at 37 degrees. But importantly, the CO2 gas that is dissolved in the blood and extracellular fluid is still there, and indeed the content may have increased. Vascular tone and carbon dioxide sensitivity depend on the total CO2 content, not the amount that's escaping from the blood. The uncorrected PaCO2 underestimates the true CO2 burden, although, in fairness, metabolism does slow in hypothermia. Patients are vasoconstricted because they are cold. Hence, we usually correct the PaCO2 to a temperature of 37 degrees Celsius to put it into numbers that we understand. Let's review this tutorial. In this tutorial, we discussed carbon dioxide solubility, I started with a discussion about extracellular compartments and fluid distribution to frame the whole picture for these two tutorials. We looked at carbon dioxide metabolism and how the production of carbon dioxide leads to some dissolved carbon dioxide in the extracellular fluid, but a lot of carbon dioxide dissolved as bicarbonate, that is a solute that cannot pass through cell membranes. We looked at CO2 solubility and partial pressures, the CO2 content of blood, plasma, and extracellular fluid, and the impact of temperature on CO2 content, in particular with respect to hypothermia. In the next tutorial, we look at oxygen solubility, and I guarantee you'll learn something.